Right, class, good morning. So just a few announcements. I hope it's in our campus already. Homework 1 is available. This is due in 2 weeks, about the session trees. This is just a tiny bit about linear classifiers in the first question that we won't, I mean, you should not, maybe you won't be able to answer it right away, but you'll be able to answer it very easily. This homework might actually take a fair amount of time. So I encourage you to start early. We'll cover almost all that's needed for a good part of the homework today and early Tuesday. So please start early. I've been told that this homework takes an unfortunate amount of time, not because it's difficult, but because it's the start of the semester and you're getting used to it. The one difficult thing about this homework, so in particular, in this homework, you'll be implementing an algorithm to train actually a few variants of algorithms to train decision trees on a certain data set that we have essentially taken and perturbed a bit from the publicly available source. So the main point of this homework is for you to get comfortable with A, implementing decision trees, and B, getting comfortable with the whole experimental part of machine learning. So there's a long description about cross-validation and what it is and how to set it up and such things. And I want you to think about that part, experimental machine learning, a bit in detail when you're implementing this, in particular cross-validation stuff. Because if you are careful with how you implement your code, chances are you'll be able to reuse it for the entire rest of the semester. So just think it through. The other point announcement is about class enrollment. Someone emailed me just this morning also. So as of last night when I checked, the graduate section of the course was still full. There were a couple of spots in the undergrad section. There may be a couple of spots in the grad section. I will talk to the undergraduate advisor after the class today. So basically what that means is if you don't get a permission code by the end of the night, out from today. So if you are, say, more than number 5 or 6 on the wait list, and you're convinced that more than 5 or 6 people are not going to drop now, I would probably say that you should assume that you're going to take machine learning next semester. Since Matia just crawled past here, I have to announce about the camera. So last lecture was not recorded, and I'm told that it's completely YouTube's fault. So on the other hand, this one I think is working-ish, working right.
Yeah, some audience calls.
Okay, there are some technical details, but it's working. Any questions about the homework or about registration or the camera? Yes. So homework be like roughly, yes. Some homeworks is, so the schedule for the homeworks is on the lectures page of the class website. I mean, there's like there are some pointers about when each homework is supposed to. You can take a look and plan ahead. We will almost definitely adhere to that schedule, but of course, given how things go in class, we might be off by a day or two. Chances are most homeworks you get 2 weeks for each homework. I'm planning 6 homeworks. In the past, I have done 5 or 6, depending on whether a certain homework they get extra time or not, based on maybe it's too heavy. 1 or 2 of these homeworks will essentially be just Canvas quizzes. When I say Canvas quizzes, again, it's like the quiz 0. So you'll get a week. You can use any material you want. It's mostly for you to revisit the things that you've seen in the class. And it's meant to be like a way for you to help prepare for exams. And the remaining will be 2-week things. The Canvas quizzes will be 1 week. Any other questions? So, if you just joined, homework 1 is available, please start it. Another announcement is about office hours. I'm almost certain that we've settled on the times and locations for office hours. We are available to help you Mondays, Tuesdays, and Thursdays. Matia and Georgi will have office hours on Mondays in the afternoon. Georgi is not here; he's joining us remotely because he has a time conflict. But he will be there for office hours, and he's available on Canvas and everything. I'll have office hours at 4 p.m. on Tuesdays, and Amy will have office hours on Thursdays at 1:30. Please note that each of these is in a different location, and that's roughly the best we can do, given some space issues. And this information is available on the class website, so you can look it up. Please do come to office. Coming to my office because we end up having fun discussions about machine learning and anything else. And I can say the same about my TAs. They enjoy people coming to their office hours as well. They're not listening, so they will say yes. Any questions about it? Logistics, homework? Yeah?
Does the runtime of the algorithm matter?
Oh, yeah. So, the runtime of the algorithm do matter. What that means is, we will run all the code that you submit. And what we want is any code that you submit, we will run it, and we want it to, essentially, the results that it gives should match what you report in your report. There's long detail about what you need to report in the homework, you should check it out. But when I say the runtime matters, what I mean is, it should finish in a reasonable amount of time. We are creating 120 homeworks, and we are going to run all of them on K8. And we want all of them to actually finish in a time that we can actually see the results. Chances are, for these homeworks, the runtime should not be too long. If it is, then there's a problem, and which means that, and what too long is depends on a few things that are not yet decided, so let's get back to that in a bit. But it should not, if it takes an hour, there's a problem. If it takes a few minutes, it's okay. And it should not take more than 10 minutes to run. Other, yes? complicated. I assume that the quiz solutions are published. Oh, okay, good, thank you. So once the quiz gets closed, the solutions will be published. Yes. Might be famous last word. I'm assuming certain things about Canvas, but I think that's how it works. And if that doesn't happen, someone send me a message. Or actually, better than someone sending me a message, just post a message on Discovery board. The quiz is not closed. There are a few people who got permission codes late, and everyone who got a permission code late, I'm giving them a full week. So the quiz solutions will be posted only after I'm assuming it gets closed for everyone. I hope. Alright, if there is no other logistical announcement, let's get back to where we were. We were talking about decision trees, and this is literally where we left it at the end of Tuesday's lecture. So on Tuesday we saw what decision trees are, and the way I introduced it, I presented decision trees not as a classifier or anything, but just as a mechanism to concisely represent a lot of data by essentially breaking the data down into features and then representing the featureized data in this sort of a tree data structure. So we looked at this example where we wanted to classify shapes, and the easy thing about decision trees is once you have built a tree, prediction is essentially like playing a game of 20 questions. Or in this case, in this tree, it's really 2 questions. But let's say you have to classify this blue triangle, you ask what's the color. That's what the first node is asking. And if it's red, you take the path corresponding to that answer. And if you reach a leaf, that's the label. If you don't reach a leaf, let's say it was a blue triangle, this kind, then you take this path here, and then you see the shape, the triangle. So this thing here is a B. Now, of course, this is you have to be careful, and this is also true for your homework. You have to be careful with how you implement this, because it's possible if you're not careful about the tree, you might end up with a situation. There's a green rectangle here. Okay, so we can answer the question, what's the color? It's green, so we go here. And then the shape has no edge called rectangle. So it breaks down. So what do we do? Any ideas? And I'm not showing you the data because I want you to kind of think about the ideas. Yes?
Can you change the order that you're asking questions?
You could, but that still doesn't prevent such a situation from happening. What is the systematic mechanism in which this can be avoided? What is the problem with this shape? With this? Yeah.
There's no branch for triangle.
Or triangle, yes. Did I say rectangle? Yeah, triangle. So there is no path from that node that is called triangle. Yeah.
So every node there has to be a kind of else category where there's no branch, then it becomes this item.
That's right.
Which you probably take the highest probability or the thing that's
the most common label. That's exactly the right answer. So what you need to do, and this actually will most likely also show up in your homework, is when you are implementing a decision tree, you should keep track of all the values that a certain feature can take. You know here that shape can be triangle, square, or rectangle, which means that you need to put out create an outgoing edge of all 3 things. So that's easy. So all you have to do is keep track of all the values that a feature can take. The next part is what goes here. And the answer that suggested was kind of the most common answer there, which is the label that goes there is the most common label. In this case, I don't remember what the data had, but the most common label among, say, anything that was green would go here. So let's look at the data. Among things that are green, you have 2 circles and 2 squares or rectangles, and you just toss a coin. And anytime there's an equality, you toss a coin. So it's definitely not a C because nothing green is there. So it's either an A or B. Let's just call this an A. So you need to, this is an edge case that you need to worry about. But given this, prediction in a decision tree is easy. You just have to walk down the tree. Yeah.
Could you look at the fact that all other triangles are in B?
All other triangles are in B. Yes, that's another strategy. Yeah. So essentially, you need to come up with a default label for every node. Yes.
What if all the features of them
Are
aren't known? Like if you don't know all the features.
Good question. What if you don't know? Maybe there are triangles, squares, and circles, and also ellipses. But you've never seen ellipses. So a generalized version of that strategy would be to have an else category, a default label. If I come to this node and I see a feature value that I've never encountered before, I follow the default category, and the default label would be something like a majority. Yes. Okay, so that's about most of what I will say about prediction. Another question is, anytime you see a new hypothesis class, decision trees, now from going ahead, we're going to start talking about decision trees as a hypothesis class, because they are a class of functions, because they can take any instance and produce a label. So anytime you see a new hypothesis class, a question that you should ask yourself is, what kinds of functions can this hypothesis class capture? Can it capture only conjunctions? Remember, we talked about hypothesis. We need to reduce the set of hypothesis classes, the hypotheses that we are exploring. So, decision trees, it turns out, can capture any Boolean function. Any Boolean function can be written as a decision tree. In fact, the first question of your homework asks you to explore this idea in a little for 3 or 4 functions. The way to think about it is every path from the root to the leaf, there are here 6 paths. Every path from the root to the leaf is a different rule. So the first path here can be seen as, if the color is blue and the shape is a triangle, that means the label is a leaf. And if the color is blue and the shape is a square, label is an egg. And so on. It keeps, basically you can enumerate every path from the root to a leaf, and that becomes a rule. And the final Boolean function is really the AND of all these rules. The function is really saying this is true and this is true and this is true and all of these are true. Together, you get the full function. This is essentially saying how to go from a tree to a Boolean function. There's also the question of how to go from a Boolean function to a decision tree. Right? So if I can show both directions, that means they are equivalent. If you given a Boolean function, if I can convert it into a tree. Given a tree, if I can convert it into a Boolean function, that means these two things are the same set. So let me walk you through an example of the process of converting a Boolean function into a decision tree. But before that, are there any questions about this? Yes.
Circle,
Ah,
square, or A, B, or C.
yes, that's right. A little bit later, I will show you how you can convert any of these things into these decisions into a Boolean function. What you need to do is consider this as true or false.
Okay, yeah.
This is true or false, and at that point, it's Boolean. Right? It's a decision, and so it's not exactly this tree. It's a different tree that says color equals blue. Yes or no? If it's yes, then you say shape equals triangle. If it's no, then you check for another color. Equals red. And so basically you can decompose it into a much larger collection of Boolean things. Yes, it's Boolean in these decisions. Good question. That's a subtle observation. Yes.
Maybe I'm missing the point, but if you're anding all of these together, wouldn't that always result in a true?
Will it? Given a certain situation, so basically what's going on here is given a certain set of things. Let me give you an example where it's not true. So I have color, what did I have? Color equals blue, shape equals triangle and label equals A. This is an instance that this function will classify as false, will map to false.
Yeah.
So if the color is blue and the shape is a triangle and the label is an A, this whole thing becomes false.
Okay.
Right? So essentially, this is a Boolean function that categorizes whether situations, labeled examples can exist or not.
Okay.
This is an example that does not fit in our world. So blue triangles with label A do not exist according to this function. Okay, so then let me now go to the other direction. Given any given any Boolean function, how do you convert it into a decision tree? And I'm going to use a simple example. And so let's say we have a function, say x1 and x2. So if you are not still comfortable with this notation, this is exactly the same as saying x1 and x2. Assume that x1 and x2 are Boolean. So they can either be true or false. So I can now say, I can just pick one of these features. I can say, what's the value of x1? If it is true, it can only take two values. It can either be true or false. If it's true, I can't say anything yet. But if it's false, this whole thing is definitely false. So the label is false. If it's true, then I check for x2. If that's also true, then the label is true. Otherwise, the label is false. So now, essentially what you're doing is you're breaking down this function into a series of tests. Every test takes you to one particular value of x, and once you get there, you apply that function on that, you kind of recursively build the tree down for the rest of the day. Pick another tree. Does this process make sense? Any questions? And if it does not, feel free to ask the question. You will be doing this for your homework also, so if you missed it here, you'll have a few more attempts.
I mean, the order doesn't matter, right? I mean, it's same as x2 and x2.
Yes. So in fact, that's a good observation. The order doesn't matter. This is exactly the same as checking for x2 first, and then putting a true here and false here. x1, and then maybe putting a true on this side and false on this side. And this is false, and this is true. These two trees are structurally different, but they correspond to the same function. Yes?
If the algorithm produces a hypothesis that isn't consistent, would the binary expression tree be unsatisfiable?
So first of all, the algorithm that we'll see will always produce a consistent tree. So that there's no but then the question still remains: if the algorithm produces, if some algorithm, not the algorithm that we see, let's say there's another algorithm that produces a tree that doesn't agree with the data. The binary, the way to think about it is the Boolean function is not unsatisfiable. The Boolean function will predict false for some example. That's the way to interpret it. But we will not have that situation in the algorithm that we'll see in a little bit. Okay, so a little bit more discussion about decision trees. In all the examples that we saw, the leaves correspond to discrete categories. There are these buckets. The leaf is a label A, or a label B, or a label C. It could be true or false. So that takes care of classification. That takes care of binary classification. If the labels are only true or false, you have multi-class classification. You have, it doesn't matter. The tree data structure does not care. Turns out you can extend this also to real value outputs, and these are called regression trees. In a regression tree, there's only a small change. The labels are not labels, but little functions that produce values. So what you do is you take a path down from, you take a certain path down, and let's say you have these leaves here, and everything here, all the boxes in this picture are labels, and the boxes are the function. So this, let's say this is x1, this is x2, this is x3. This could be some function that says x1 plus x2 minus 3. And suddenly you can produce real numbers. So this is like the sketch of an idea for how decision trees could represent real numbers, except you have to decide what these functions are. So that makes the learning a little bit more sophisticated. Decision trees are really old. So there's been a lot of work on how to handle noise, how to handle missing data, how to handle missing features, how to handle incomplete data sets, and so on. And we'll explore at least 3 or 4 of these directions in a bit. But if you want to spend your time learning about everything to do with decision trees, I think we'll spend our entire semester doing that. So if you want, I can point you to references afterwards. Okay, so another thing that I want. Did you have a question?
I do have a question.
Okay.
So decision trees with discrete categories are supposed to be right now like memorization and not generalization.
Yes.
So if something doesn't know,
There is no generalization yet.
okay.
So in fact, that's also a very good observation. So far, all I have told you is you have a data set and you just transform the data set into a different form that corresponds exactly to that data set. How is there any generalization? The only hope for generalization comes from, it almost seems like there's no generalization. The decision tree is just remembering the data. And in fact, that's what happens if you let your tree grow arbitrarily deep. Then it will essentially memorize every little nook and cranny in the data, it will memorize the noise in the data, and so on. So the strategy that I will get to hopefully at the end of today's lecture, if not at the beginning of Tuesdays, is how do you generalize? And the way to generalize is we don't let our trees grow as deep as they want, or as tall as they want, depending on how you look at the trees. Instead, we just prune them. We limit the depth of the tree, and as a result, we are essentially making an assumption about the nature of the function, the complexity of the function. We don't allow arbitrary Boolean functions, but we allow Boolean functions that are only so complex, and that complexity corresponds to the depth. We will talk about this at the end. Yeah.
You stated that any Boolean function can be converted in decision tree.
Yes.
How do you prove that?
It's a procedural thing. Essentially, any Boolean function, you recursively pick a variable, and you create a node for it being true or false. If it's true, you have you plug in the value true in that function, and you get a Boolean function without that variable, and you recurse. And you do that on both sides. If it's false, you plug in the value false, and you recurse. And that gives you a constructive proof. I've given you a sketch of a proof. Think about it, and you should be able to formalize it. Yes.
Could an answer to that be like given any Boolean function, we can convert it into a form with only conjunction, and then we can.
Yes, that's the other answer. Any Boolean function can be written as a CNF, a conjunctive normal form, and then you can explore that, but that doesn't always work out, and you have to be a little bit more careful with that proof and think about why. Okay, so the next question is, remember when I talked about features and stuff, I mean, who said features can only be Boolean? Who said features have to be discrete? Maybe features are real value. How would this whole system work if your features are like the height of a building or the depth of a swimming pool and things like that? These are real numbers. How do we deal with real numbers like length? One answer is, or in some sense this is the only answer, is no matter what you have, you need to discretize things somehow. You need to discretize your real space into discrete categories, because you can't have tests of the kind length 1.1, 1.11. Yeah, you see how this is going to fit. Problem is the number of real numbers is infinite, and you can't have infinite branches coming out. So what you do instead is you discretize the numbers. So here's an example. Let's say you have two features, x and y, and let's say this data says this whole region is minus, this region is minus, and everything else is plus. What you do is, instead of directly using the values is you convert it into a series of tests for the values of these things. So instead of using the value of x as a feature, the test becomes, is x less than 3? If x is less than 3, you are talking about this region. If x is greater than 3, you are talking about this region. Inside this region, where x is less than 3, you can ask, is y less than 5? Y is not less than 5, simply you are in this block, and the label is a plus. So essentially, you can create the whole point of this is any continuous function, you can have a piecewise approximation, and by building these pieces carefully, you can represent the function. The higher level point is decision trees give you decision boundaries that can be non-linear in the feature space. This is the first instance that we'll encounter of non-linear models. And at this point, I've not told you what linear models are, and if you've not seen them, it doesn't seem like a big deal. The reason it's a big deal is because linear models are extensively studied in machine learning. Linear models are models where decisions have to be aligned. The boundary between two classes have to be aligned of this kind. Everything on this side is positive, everything on this side is negative. This is not aligned. This is a more complex object, and decision trees can represent more complex objects in the space, in the feature space. Yes.
Can we have more than 2 branches at each of the nodes?
If you can define a test of that. It's usually not, anytime you have more than 2, you can always binarize it, and learning becomes easier if you binarize it. In this case. Other questions?
How do you decide the order of the?
We will talk about it. Yes. That's a much more subtle question. How do you know these are magic numbers? 3, 5, 7, 1. How did they come? Where did they come from? And there are a few heuristics for it. One heuristic is you divide the space into uniform. What do you call it? You divide every feature uniformly into buckets. Another heuristic is you introduce a partition along this axis every time two examples change a label. Every time a certain label changes along that dimension, you introduce a partition because those are the only places where the data can possibly give you any information. There are other heuristics. Another heuristic could be you kind of look at the histogram of all the examples in the space along each dimension, and you carefully, cleverly decide. So at that point, cleverness comes in, which means generalization to other problems goes away. The software packages that use decision trees with numeric features typically use one of the first 2 strategies I talked about. Either just bucket the feature, essentially bucketing features either uniformly or non-uniformly based on how features change values. How the examples change values. Okay. Just to quickly summarize what we saw about the representation part of decision trees. Decision trees can represent any Boolean function. In a kind of course, we are saying that decision trees are just representations of data that also happen to be predictive functions. It's in some sense a very natural way to represent data. We've been playing 20 questions. Kids play 20 questions all the time. What they are doing implicitly is essentially walking down the decision tree. So it's a natural mechanism for categorizing data, and that's the reason why I'm unable to find a reference of who invented decision trees. Predicting with decision trees is also very easy. All you have to do is walk down the tree. In order to kind of think about this a bit more, I want you to kind of think about this point that given any data set, there are many decision trees that can represent it perfectly. There are many decision trees that can perfectly capture the same data set. And I'm not going to talk about the answer. I actually did already talk about the answer a little while back, but think about why and maybe prove it to yourself using a tiny data set. The next question that we need to address is how do we learn these decision trees? So given any hypothesis space, the questions you need to think about are, what is this hypothesis space? What class of functions does it capture? How do you predict with this hypothesis space? Given a function from this hypothesis space, how does that function take an input, an instance, and produce a label? The how really encodes two different parts. One is what's the mathematical form of that prediction function, and the second one is what is the computational aspect there. What is prediction is so expensive computationally that you're not going to use the hypothesis space. So prediction has two parts. The third thing that you have to think about when you think about a new hypothesis space is how do you learn with this hypothesis space? There is no one answer for any hypothesis space. If I just tell you decision trees, there are many learning algorithms that for exploring this hypothesis space. We'll just look at one of them and a few variants, but you could invent a new one tomorrow that outperforms all of them. And similarly, when we talk about say neural networks, linear classifiers, and all of these, there are many learning algorithms that explore the same hypothesis space. So, questions for any hypothesis space should be, what's their expressiveness? How does prediction work? How does learning work? These are the three basic questions you should always ask yourself. And then there's another meta question that always comes up, which is, okay, now that we have the Platonic ideal for all these things, how do we take this hypothesis space, class of functions, and make them work with real data? What are all the tricks and tips and dirty hacks that we have to implement in order to actually deal with real data? So we'll talk about that once we finish the learning algorithm. And there are all these mathematical ideal functions and learning algorithms, and then there are all the dirty things that you need to do in order to make them work with real data. Throughout the semester, what I'll do is I'll introduce many different hypothesis spaces, many different learning algorithms, and talk about the practical heuristics that tend to work. And in your homeworks, you might have to actually employ many of these practical heuristics because you will be, as the semester progresses, be dealing with more and more noisy data. Hopefully, towards the end of the semester, you will realize that there is an equal importance of these both the practical aspects and the formal aspects of the learning algorithm. Throughout this lecture, I kept talking about various exercises. I just wanted to put them on one slide. When we looked at the shapes data, I wanted you to write down a decision tree. We picked one decision tree for this data. What I would like you to do is write down another decision tree where the root node was different from what we saw in the class. Just to convince yourself that there could be another decision tree that predicts the same thing. The question that then comes up is, there seem to be two different trees that agree with the same data. Would they also agree on all future examples? Think about this, and some of you in your answers hinted today that you think not, and some of you hinted that you think you do. More generally, I would also like you to think about this question of how two different, the same Boolean function can have multiple trees that represent the same function. So think about this, prove it if you want, and along the way you need to think about what it means for two decision trees to be different. Is it just how they are drawn? Is it just the ordering of the nodes? And when you think about this, you will appreciate the pain that my TAs have to go through when grading your decision trees, because the same question has multiple correct answers. Awesome. Alright, let's now move to the next question, which is learning. I'm going to talk about a particular heuristic for learning a decision tree called the ID3 algorithm. But very briefly, history of decision trees is it goes way back. I think the earliest recent work that I've seen in this actually comes from psychology, where there was some discussion about how concepts are learned by people. The earliest sort of machine learning or computer science sort of work in the space was done by Ross Quinlan in his ID3 algorithm. ID3 has a really cool name, the iterative dichotomizer tree. It almost sounds like a movie title. The ID3 algorithm is from the 1970s, which is what we'll look at, and it uses some ideas from information theory, and it was really the driving force behind a lot of, when I say it, I mean it and its variants were the driving force behind a certain wave of artificial intelligence called expert systems, which it turned out didn't work out quite well, but we'll encounter this quite a bit. Along the same time, about the same time, or just a little after Quinlan's work, Leo Breiman and Jerome Friedman and others from statistics developed a class of learning algorithms called CART, classification and regression trees, that look kind of similar to ID3 but use slightly different heuristics. Now these two families of algorithms were kind of well established, and throughout the 80s there was a lot of work on how to make them practically useful, how to deal with noise, how to deal with real valued features, how to deal with real valued outputs, what do you do when you don't have certain data, what do you do when you don't feed certain features, and so on. And a lot of this work is pretty well established. Along the way there were updates to these algorithms. Today, if you use a decision tree package in say Weka or scikit-learn, chances are they are some descendant of the ID3 algorithm like C5 or C4.5, but we won't look at C5 and C4.5 in this class because they are essentially subtle variants of the core idea. So we'll look at the basic idea and you'll be implementing that. Now, decision trees seem like a very old idea, and they seem boring. I mean, boring in the sense of they're not fancy and modern, and you don't see them in the news. The New York Times does not definitely talk about decision trees like it talks about neural networks. So one question could be, why does it matter? Why do we still need to learn about these 1970s things? And one answer, which I think is, actually there are two important answers here. One is, today, decision trees may be the most interpretable of machine learning algorithms or machine learning classifiers. When I say interpretable, I mean if a system predicts a certain label, you have an audit trail. You have a trail of decisions that led to that particular label. So you can always go back and ask, why was this particular example classified as true? Why did this image show up in my inbox and not in the spam box? And you have a series of choices that led to that answer. Decision trees naturally have that. Neural networks and pretty much no other system has that. So that's one answer. Interpretability is a big deal when we want our AI systems to actually, say, stand up in court and take liability. The second answer is, even though decision trees by themselves may seem a bit outdated, which, at least in some pop culture sort of sense, variants of this core idea in the form of boosting and bagging, these are essentially ensembles or committees of decision trees, tend to be extremely robust. They tend to be really good classifiers, even on par with the latest and the greatest things. There was a paper from the 2005-7-ish by Rich Caruana, who is currently at Microsoft Research, who in that paper compared, it was this massive empirical effort that compared every possible learning algorithm they could think of on every possible data set they could find in 2007. So it's like a huge empirical effort. And they found that essentially if you have fewer than, say, the very, very high level message from that paper, if you have fewer than, say, about 300 or 200 features, all of which are discrete, you would be hard pressed to find a classifier that is better than a committee of decision trees. Not one decision tree, but a committee using boosting. We'll encounter boosting midway through the semester. So the point of this whole slide is it's still worth learning about decision trees, and things get reinvented all the time.
So you're saying this could up to 300 features, and after that, then you have to go to a different model?
Yes, that was the message of that paper. It's worth reading that paper. I'm giving you just the highlights of that. There are subtleties, and it also depends on the kind of the data and such things. But they are extremely good black box learning systems if you don't want to think about the problem. So there is this trend towards going towards black box learning systems. You want to take your data and give it to a black box, and it gives you a system. Decision trees, boosted decision trees tend to be one good thing. Multi-layer neural networks tend to be another good thing. So, in order to introduce decision trees, I'm going to steal an example from Tom Mitchell's textbook on whether I guess, or Tom should play tennis today or not. In order to decide this, of course, you can always go outside and decide whether you want to play tennis or not, but we are computer scientists. We don't go out. Instead, what we'll do is we will get features. We will look at the outlook for the day. Is it going to be sunny, or is it going to be overcast, or is it going to be raining? We look at the temperature. Is it mild or cold or hot? We look at the humidity. Is it high, humid, or normal, or very dry? And we look at the wind conditions. Is it strong or weak? Based on these 4 features, we have to decide whether we want to go play tennis, which is the label plus, here, or we want to not play tennis and do something else, which is the label minus. So this is the general setting of the problem. Notice that what I have done here in this slide is define the instance space as the cross product of all these features and the label space, and in some sense describe the problem field. What is the goal of this problem, of this classification task? In true machine learning sense, in the true machine learning style, what we can do now is keep track of when you play tennis and when you don't, so that you discover some regularity. So let's say that we have 14 days of data. So the way to read this table is on a certain day, on day 9, say for example, the outlook was sunny, the temperature was cool, the wind was, the humidity was normal, and the wind was weak. And it just so happened that on that day I played tennis. So you just record this. So this is the data we have. The goal now is to build a decision tree using this data. Before we actually see the algorithm that we'll see is a batch algorithm. What that means is it processes all the data together. You need all the data. There's this machine that takes all the data and produces a tree. It does not. The alternative to that is you see one data point at a time and iteratively update the hypothesis. Now here it takes all the data and it produces the tree in one shot. And internally, it is a recursive algorithm. It recursively builds the tree from the top down. So it first chooses. So that means that all you have to do is you need to decide what feature goes at the top, and what to do for each possible value that the feature can take. Because once you make those 2 decisions, you need to build a little subtree inside each of these things, and you can call the same procedure again. What feature goes on top and what to do for each value. So it's a recursive process. So the algorithm that we'll encounter is a recursive step that consists of 2 steps or 2 parts. A choice of what attribute to split on and a decision of what to do for each particular value that the attribute can take. Yes?
So I don't know if this has to do with this particular data set, but say if you given 2 days with the same features.
Mm-hmm.
One day you play tennis, and the other
you did not.
Would we use something else then?
No, you could use this. What you'll get is a tree that is not consistent with the full data. Because so essentially what you're saying is, so just to kind of rephrase the question for everyone else, in this data that's not going to happen, but suppose you had an example S, H, H and W, where on day 1 it is minus, and on day 15 it's a plus, for the same set of observations. this algorithm will basically choose one of them.
So we're just missing a feature.
We are missing a feature, or there is noise in the label. Maybe the choice to play tennis on the 15th day was a bad idea. Maybe it was just a bad day to play tennis, and so there's noise in the data. And we'll talk about how to deal with noise in a bit. For now, we are going to assume that there's no noise in the data, and the data we have is clean, just to kind of set up the algorithm. Okay, so yes.
So going back to that tree that you're going, you have to choose. Okay, so how do you effectively select the first?
How do you make these decisions?
Yeah.
Yeah, that's the question. That's what we look at now. That's really the question. That's basically all there is. So, what you're asking is really, let's talk about the algorithm. Right? So let's talk about the algorithm. The ID3 algorithm is one of these nice algorithms that is very compact. What I mean by that is it fits in one slide. So let's consider two different parts of it. Suppose, let's first deal with all the easy cases. Okay? So the input to the algorithm is a set of examples, set of labeled examples. And let's say the goal is to predict one of these columns, the label. And the attributes are all the features that we have. So the label is just the name of that label. So is it play tennis? So you have a data set, you have a list of features, and you know what to predict. Now suppose the easy case is, suppose all the examples in the set S have the same label. You can check for that. If they have the same label, then problem solved. All we need is to produce a leaf node with that label. Right? You don't need to test for anything because the entire data is you just need to predict whatever that label is. So that's easy. So that's the base case for the recursion. Otherwise, we need to do something else. We need to create a root node. We need to decide, when I say create a root node, what I mean is you create an empty node with that we are going to fill in an attribute. So we've created a root node. And that's the root node that we will return at the end, because the tree is entirely decided by what comes below it. So if we return the root node, we've done everything. So the next decision is we need to decide what goes inside. I'm going to abstract that out for now. We need to decide an attribute that goes into the root. So in the example that I had, we need to decide. So what was that? What was that I picked? So it was outlook. We need to decide that outlook goes here. And our choice of what we pick here would decide what we do next. The way we decide what goes there is we need to somehow, and we'll talk about this quite extensively in a bit, we need to somehow decide which feature best classifies the entire data. If we had a single feature that classifies the entire data perfectly, that's great, because we've essentially hit upon a small tree that gets you the label. So we need to somehow decide the best feature, and best is decided by, we need to find the feature that best classifies the entire data. And if we had some process for that, the rest of the algorithm kind of falls in place. Because imagine that feature can take multiple values. So that attribute A can take multiple values B. So if you have outlook, it can take, I don't remember what the three labels were, it could take 3 values. For each of those values, we need to now do something else. So for each value, we need to create a branch that that value can take, that attribute can take, and then what? So notice that we have a set of examples here. Right? This was the set that we used to create this, decide on what feature to do. When we go down this branch, necessarily there's going to be a subset of those examples that fall inside that bucket. Right? So let's call that subset S. So we have a feature value B, we have a subset SV. SV is also a set of examples. Right? SV is a set of all examples where the outlook took a certain value. So what do we have? We have a set of examples and we have a set of attributes that we can use. All attributes except the one that we just picked. We have a set of examples, we have a set of attributes, and we need to produce a tree that gives us that label, gives us that, that agrees with all those examples. Do we have an algorithm for producing that? Yeah. So we have a set of examples. First of all, we need to decide what to do if that set of examples is empty. Maybe there's a certain path, maybe this particular path, there is no example in the set S that takes this feature. This was the green triangle that did not show up in our training data. What do you do with green triangles? If that's this is exactly what happened, right? I mean, there were no examples in that particular case. What you do is you add a leaf node with the most common label. That was the suggestion that was offered. And can someone who did not, I think you made that suggestion, right? Someone who's not him, give an answer for why. Why this is a good idea. Yes?
I feel like you have to choose which one weights heavier out of the set that would fit in that.
Okay, can you say that again? Which one?
So like let's say you had multiple like for one specific node,
Yes.
you had multiple values.
Yes.
They were different. You want to take the one that you probably want to choose the one that appears the most frequently.
And what will that give us? So the question, just to kind of reiterate, is I have chosen a certain attribute to branch on, and now I go down this path for V1, and I find that nothing in my entire data, no example in my data has the value V1 for that particular attribute A. And I'm arguing that at that point, you can't just give up your hand, give up and go. What you do is you add a leaf node with the most common label inside the set. How is it going to help us? Yes.
Most probably be right.
You'll most probably be right. Right? I mean, I don't know what will happen there, but until when I came down to this particular node, among these examples, among all the examples that came down there, the most common label is, let's say, true. Then I just say true. Chances are I'm going to be right. At least that's the most likely value that it can take in a certain formal way. What that gives us is it gives us some amount of generalization. For instances that I've never seen before, I'll most likely be right inside that bucket. So that's the easy part, so to speak. Yes?
So for the part with where we choose the attribute that best classifies the S,
Yes?
are we actually ranking all attributes?
Yes? Among all the attributes that were given to us, we're going to rank them and find the best. Okay, so then we handle the case when I'll get you in a minute. We handle the case when the set SV was empty. The next thing to do is when SV is not empty. So now what we have is we have a set of examples, SV, which is not empty, and we have a set of features, which is all the features except the one that we've already used up, and we need to build a tree. What we need is an algorithm that takes a set of examples and a set of features and gives us a tree, and luckily we just happen to have one. The algorithm that we are building. So we just make a recursive call to the subset, using the subset. And that gives us a tree, and we just attach the tree that ID3 gives us at that point. You had a question?
Yeah, I was just wondering if there's any alternative methods to generalization. So rather than pick the most popular
Yes.
label, pick the most popular label given your first attribute.
Yeah. So this is just one of the different strategies that you can use. You can try different values. So you can pick the most popular label in the entire data set that you started off with, because there's a recursive call here. This could be 8 deep inside a recursion. So you could pick the most popular label somewhere else. You could have some extra knowledge, or even better, at that point you could put a little function that tosses a coin and predicts based on tosses a unfair coin based on whose probability of, say, picking a label is somehow dependent on the distribution of the data and picks a label randomly. So there are multiple strategies you can use. What I have here is the simplest one. Yes?
So on number 2, you say H. You pick an attribute that's classified as X.
Uh-huh.
How do you know what that is?
We will get there in 1 minute. That's really the biggest decision that we need to make. Yes, I'll get there. That's the next thing we'll do. Yeah.
I have a question regarding updating the tree. So when a new data comes after a week, for instance, right, we want to update the tree to be more correct with the old data that's seen before.
Yep.
So now there are 2 questions. First, is there a better way to update the tree than to rerun the whole algorithm on the whole data again? Like if there is more.
So the version of the algorithm that I'm presenting. Okay, you had 2 questions. What's the second?
And the second one is, how do you decide when to update the tree?
Okay, let me answer the first question. So the question was, let's say now I have trained I have a large data set with 1 million examples. I have trained a tree, and now I use the tree, but I also harvest more data. Next week I find 1 million new examples. Now I have 2 million examples. Do I need to run the whole thing again, or can I make some edits somehow to just fix the tree? The kind of boring answer is no, you have to run the whole thing again. The version of the algorithm that I'm presenting here, you have to run it again because it does not show any way of editing. The somewhat more subtle answer is you can do a few variants of things. So for instance, one thing you can do is you don't need to update the whole tree. Maybe you can update only sub-trees that that need to be changed. You can make localized edits based on the examples that add more information. At some point, you might have to essentially rotate the whole tree because after getting 2 million examples, maybe you realize your choice of the route was all wrong. At that point, you don't have any other go. Another thing you could do, and this is what's done in the more sophisticated version, is you take the tree. After training, you take the tree and you convert it into a set of rules in Boolean algebra, and then you essentially edit the rules. Then it becomes an easier editing operation. So there are a few variants. So that was the first question. The second question was, how do you know when to update? I don't know. You have something that's dependent on the application that you're building. I don't know. I don't have a good answer. Did someone else have a question? Okay, Brian.
What happens when you see a scenario where B is not in the tree?
When B is
the value of the attribute.
So yes. So this is this is a good question. So this is a question that let me zoom in here so that I can have some space to draw. So I have a data set S, and are you talking about prediction or training?
Well, training you see the value.
You would see all the values.
Prediction would not.
Exactly. So let's say that during training I saw some attribute. Let's say I have an attribute A, and it takes, say, triangle, circle, and square. And I built a tree. And what it does is it can be triangle or circle or square. And at test time, I see an example that has A equals. I've exhausted the list of things I know how to draw trees. So let's say an ellipse. What do? Often a good thing to do in these kinds of situations is to have a default edge while training. You always have a default edge, which is other. And you put a default label, which is like most common label. So you assume, so there are 2 ways to go about it. One is to say, suppose you know that these are the only 3 shapes that you can ever get. Like Boolean, for example. If your feature is Boolean, you know it can either be true or false. There is no other thing. So you've exhausted it. In which case, you don't need the default label. In all other cases, it's often useful to have in your implementation a default edge that comes out of every node, and there the value is the most common label inside the set of examples that was used to produce. Does that? There was another hand that went up somewhere here, and then I'll get to you. Yes.
With the
most common label.
Yeah.
During testing, if it finds that what it picked is wrong, would you basically just make it so that it just goes to the next most common thing, or
How do you know that it's wrong?
say the test data?
But the test data is future examples. You don't have the ground truth.
Okay.
So I mean, I'm just being a little bit annoying with my questioning here, because in the limit you will run into situations where you don't know the label. Then imagine that you have an email that the spam detector has to decide whether it's spam or not before you see it. Before you see it, it does not know what the label is. There is no correct answer there. Meaning there is an oracle, there is a ground truth, but nobody has access to it until you actually see the label. Which means there is no way it knows whether it's correct or not. Which means it makes the decision and it eats the error. It has to live with that's basically the classifier errors. I'll get you in 1 minute. I think you had your hand up.
So we just have a question about this example. So what you're saying is that the training data only has a certain amount of features,
certain values,
and then you get an example that has a different value from the training data, and you just basically send it down the default path.
You could, yes. That's assuming that you are allowing the set of values that the features can take to grow. There may be certain features that cannot take more than the values that any other value. Like the best example of that is Boolean. A Boolean feature can only take 2 values. If your feature test is x greater than 3, true or false, x is either greater than 3 or it's not. There is no other value. In those cases, you don't have to worry about. It's a closed set of values, so you don't have to have the default category. Having it's not going to hurt. You're just adding a little bit more memory.
So does that mean that the decision algorithm can change based on what you know about what your label is going to be?
Yeah,
As in, if you know that every label is only going to be a Boolean, then you wouldn't have to construct the other.
Yeah, you could. You can choose not to, and it will be fine. Whereas, yeah, you're right. I mean, these are all little flags that you can have in your implementation. I saw a few hands. I don't remember the ordering. So I've never heard your voice or yours. So you go first.
All right. Back with that spam example.
Yes.
How can you tell if it's wrong? Would a possible solution to kind of add to the examples subset be
and then retrain.
You kind of have it ask if this is not spam or not.
And then you need to retrain.
Yeah.
Right. And that goes back to the question of when do you retrain? Yes. That's essentially the answer. Yeah.
Would it be a good practice to, if we encounter something like an ellipse, can we say that it's most closer to the surface? So can we go down the path of the surface?
But that means that you need extra knowledge about what most close is. So yeah, I mean, if you knew that, that's a good thing to do. But you need to somehow bring in that extra knowledge. That is not in explicitly the features.
So is this the way? Is this the same way we handle null value?
The what values?
The null value.
Where?
If let's say they have a row that the attribute A.
Oh, I see. If it's missing.
It's missing, yeah.
We can. This is one way of doing that, but there are slightly more interesting things that we can do, and we'll definitely not get there today, but we'll get there on Tuesday. Okay, so what? Let's think about this algorithm. As many of you pointed out, the most important decision that is that we have not talked about in detail is this question of how do you pick a root attribute? Because if you can do that, everything else kind of falls into place. So really, the most the pressing question that we have to decide is this ordering of features. Here we can introduce some sort of inductive bias that we want our trees to have, or learning algorithms to have into this process. One good inductive bias. But when I say inductive bias, what I mean is we can introduce sort of knowledge about how we believe a good decision tree should look like, what kind of properties it should have. A common inductive bias that is pervasive across machine learning is Occam's razor. We want the simplest explanation possible for the data. But then that's just pushing the question of what is from best to simplest. What does it mean to be simplest? In decision trees, there's a natural notion of simplicity. I want the smallest tree possible. And that's actually a pretty intuitive idea, because I want the smallest tree possible, because if I can find a small tree that perfectly explains the data and a massive tree that also perfectly explains the data, the massive tree is probably fitting some noise. You know, it might accidentally use features that are noisy. So you want to use as few decisions as possible to construct the output. So Occam's razor is a good guiding philosophy here. Unfortunately, finding the smallest decision tree that's consistent with the data set is intractable. It's NP hard. So then we can't, it's computationally not possible. As a result, what we have here is the recursive algorithm that we have is a greedy heuristic that we can somehow influence by controlling the definition of best. Keep in mind, this is a greedy heuristic. We are not searching over the space of all the possible trees. Once you make a decision for the root, you're never coming back up and saying, oh, you know what, my choice was wrong. Let me now change the decision for the root and come back and change something. So once you make a decision for the root, you recurse and you keep building the tree down. So this is greedy. There is no backtracking here. If those of you who've taken AI who recognize that this is just a search strategy. So the main decision that we have is deciding what attribute to split on, and we want to incentivize small trees by some means or other. So let's look at an example that we can use to kind of get an idea of what to do. Suppose you have a data set where you have two features, A and B. Let's say these are all Boolean. And let's say you have 200 training examples. Among these examples, 50 of them, in 50 examples, A is 0 and B is 0 and the label is minus. In 50 examples, A is 0, B is 1 and the label is minus. You have seen no examples where A is 1 and B is 0, and you have 100 examples where A is 1 and B is 1. This is a data set. You have 200 examples of this kind. So then, a natural question, the question that we really want to answer is, should you split on A or should you split on B? Let me, instead of asking you to answer that question, let's actually just explore both cases. What happens if you split on A? If you split on A, it just so happens that whenever A is false, the label is A is 0, the label is minus. Whenever A is 1, the label is plus. You get this tree. This tree perfectly agrees with all 200 examples. If you split on B, what you get is when B is 0 here and here, the label is minus. You just have never seen this case. You've never seen this case, so you can't say anything about it. But among the examples that you've seen, when B is 0, the label is minus. When B is 1, you still have to test the value here. So what happens is, when you split on A, you get what could be called purely labeled nodes. Meaning all the examples so you have a set of examples with 200 elements here. When A is 0, you get 100 examples here, which are all minus. And when A is 1, you get 100 examples here, which are all plus. So basically, all the examples here, this is both plus and minus. So all the examples in each direction is purely labeled. This is the base case of the ID3 algorithm. And this also seems to, and hitting the base case means you're not going to grow the tree anymore. So if you get purely labeled nodes, seems like the tree is going to be shorter. That seems like a nice thing. Let's break it. Suppose instead of this situation, you have exactly 3 examples where A is 1 and B is 0. Okay. Now the question is still, it's still valid. Which attribute should you choose? If you choose B, we get the same tree that we had before. If we choose A, we get another tree that looks exactly the same. The depth of both trees is 2 or 3, depending on how you count. You basically have 1 step and 2 steps. So both trees have a depth of 2 hops. Which one do you prefer? So now, the two trees are structurally identical. They have the same depth. So, the question is, which attribute is better? And I'm arguing that A is better still, and I want someone to either agree or disagree. Yes.
A is better because statistically, you've got 100 choices that are going to result in just going down one level when you reach a weak node. So at least half of the learning cases, you go one step down and you're done.
So the answer is in A is better because in half your data, with just one decision, you have answered the question. Whereas here, with one question, you've answered only 1/4 of the example. You've correctly labeled only 1/4. Does anyone want to argue for B? Usually, I always have at least 3 people who argue for B with interesting answers. I mean, I'm not saying that the answers are wrong, because remember, at this point, these are, in some sense, design choices that we have. We can choose to create a scheme that puts B on top. We can choose to create a scheme that puts A on top. So does anyone want to argue for B?
Yes. It could be the case that it's harder to evaluate B, right? It takes more time. And
Okay.
then you want to have a left tree, because then in 50 cases you will get the answer immediately.
Actually, you just argue for A. Because if you say it's harder to evaluate B, you want to avoid evaluating B.
Yes.
I think what you were going to say is maybe it's harder to evaluate A. Maybe A takes a week to compute and B takes 1 day to compute, or B takes a second to compute. In that case, you have to wait a week no matter what. Here, at least in 50 of them, you get the answer quickly. That's a good reason to pick A or not pick A. Did you?
Yeah, no, I was just gonna say, like, the only way I can see it if the 3 example exponentially increases, that's the only way to look at it.
Right, so it's a computational argument. Yes, there was a hand.
Your strategy is great because you sort of quickly determine what the correct altitude is quicker.
Yes.
But it seems that we should also take consideration like what is the most accurate.
Right. So there is quickness with respect to time, how fast you get to the answer, and then there's also whether it's correct or not. Here, I think these two things seem to coincide, because it's not just quickness or not. In fact, in both cases, so there's quickness with respect to how long it takes to compute the value of A and B, but there is actually, I'm arguing that there's also accuracy benefit here, because in a majority of the examples, so there's an accuracy benefit if you are willing to buy the idea of approximation, which is a choice. So in a majority of the cases, the decision is simpler, which means chances are it's probably more correct. That's the philosophy of approximation. With a fewer decision in 100 out of 203 examples, you have essentially resolved all the uncertainty. Here, in only 53 out of 203 examples, with the same number of decisions, you have resolved all uncertainty. So you have, by picking B, you are keeping the uncertainty alive for long. By picking A, you're getting rid of uncertainty as quickly as possible. You're reaching a decision quicker. And as a result, in most examples, even in the future, you will get rid of uncertainty faster. And when I say faster, I don't mean in the time point of view, though that's also true, In most cases, the uncertainty is resolved with fewer decisions. And that's, in some sense, an intuitive answer for why it's better to pick A. This is perhaps the idea that is captured in the ID3 algorithm. The most popular heuristic for building decision trees essentially is deciding what is this decision. How do you pick the next attribute? And it uses this heuristic that's called information gain. Information gain is the heuristic that was in some sense invented for the ID3 algorithm. And given that there's only 1 minute left, there is no chance I'm going to finish that. So what I would encourage is I want you to kind of go ahead and read the slides. I'll revisit them again, but I want you to kind of read the slides because if you have never encountered the idea of entropy before, if you've never seen the idea of entropy before, you might find it to be a little bit tedious. So if you've never seen entropy before, just read up a bit on that. If you've seen entropy before, bring it back to the top of your stack so that you can build on it. And we'll get here.